So a perceptron is a simplest classifier, but this brings us to the question, can a single neuron really learn something? Can we perform any task using one single neuron? So let me give you an example. Every day you get lunch at the cafeteria and there are only three things that you eat, either fish or chips and get some drinks with it. And you get several portions of each based on how hungry you are today. So the cashier only tells you the total price of the meal. You don't get the actual breakdown. After several days, you should be able to figure out the price of each portion. By now, you know that if I take 2 portions of fish, that costs me more than if I take 2 portions of drink. Okay, so on and so forth. So there is some idea that starts formulating in your head about the actual prices. So each meal price gives a linear constraint on the prices of the portion. So basically, the total price of your meal tells you something about the prices of each of the individual portions. So what I can say is the total price depends on how much fish you took, how much chips you ate, and how much drink you got. And then what the individual weightages of these would be. So the weightages in this particular case would be the prices associated with each one of these. So the prices of the portion are like the weights of a linear neuron. So each portion along with its price would determine the overall price of or cost of your lunch or cost of your meal. We'll start with the guesses of the weights and then adjust these. So in the beginning, what we do is we just have some idea. Maybe fish costs me 100, chips cost me 50, and maybe drink costs me 50, or maybe all three of these cost me 50. And then we keep on adjusting this until we get to some form of or some final solution. So here is a basic idea of what goes on inside the cashier's brain. He understands that you've taken some fish and some chips and some drink, and he tries to evaluate the final result based on this. So I took 2 portions of fish, 5 of chips, and 3 of drink. Understand that these 3 values over here represent your x values. So I'd say x1 is equals to 2, x2 is equals to 5, and इसी तरह x3 is equals to 3. So the next thing that we need to figure out in order to calculate the final result is the value of w's associated with it. So we arbitrarily assign some weights. We say maybe w1 is equals to 50 and w2 is equals to 50 and w3 is equals to also 50. And then we perform our calculation and get the final result. Now the meal price calculated by our model is 500. Whereas the actual price was, let's say, 850. Since we are working in the supervised domain, so we do have the actual prices. So we do know that given these portions, the final result should be 850. This ends up or gives us a residual error of 350. So the next thing that we do is we apply learning rules and update the weights. We understand that the result calculated by our machine was incorrect and we fix the weights in order to reduce the error. Okay? It's the same thing we did in linear regression. We fix the weights in order to reduce the error, and we bring it as close to or equal to the values that are actual. So we bring the predicted values as close to the actual values as is possible. So this is where we end up. We've got some values of x, we've got the weights fixed, and based on the fixed weights or the adjusted weights, we now have the correct value of the final or output result. So the concept of a perceptron was given by Frank Rosenblatt in 1958, where he showed that one single perceptron can be used or trained as a classifier. Later, these perceptrons or neurons were grouped together to form a complete artificial neural network that can perform a lot more complex tasks than a single neuron. However, This is what a single neuron looks like. We've got some inputs, x1 and x2. We have some weights associated with these. We perform some linear combination of them. And based on this linear combination, if it's greater than threshold, then there is an output, otherwise not. And the points to note over here are that a perceptron usually takes any number of input. What I'd like you to remember is there is no limit on the input that a perceptron takes, but the output must be binary. Okay? There are two important things over here to remember. Several inputs, however, single binary output. Okay? So it can handle only two class problems, nothing more complex than that. The model consists of a linear combiner following by a thresholder or hard limiter. Linear combiner, we just discussed it in the equations that we had, that what it does is performs the weighted sum of all of the inputs, and at no point do you see a power to any of the inputs. So this is simply a linear combination of all of the weighted inputs. Then these inputs are applied to some threshold hard limiter, and it produces output equals to +1 or -1 if it is less than 0. So here what we are concerned with is the sign that is produced. So the output or the y depends on the sign that we have. If the sign is equals to positive, we'll say that this belongs to one class. And if the sign is equals to negative, then we'll say that it belongs to the other class. And the assignment of sign depends on what the activation function gave us. So if the activation function produced anything greater than 0, then we get output equals to 1, which would be the first class. If it was less than 0, output would be equals to -1, it would be the second class. Now here is an example of a simple neuron. There are two inputs, x1, x2, and here is the x0. There are three weights assigned to x0, x1, x2. x1 has a weight w1, w1 equals to 1, w2 equals to 4, and w0 equals to -10. So if I can put it in the equation, this is what I'd write. W0, w1 x1, and w2 x2. Now rewriting the equation, I get this form, x1 equals to -4 x2 plus 10. If you look at it closely, this is the equation of line. So this is the first dimension. You can call it y if it's simpler for you. And this is the second dimension. And based on the inputs of this dimension, you can have the values over here. So we can plot this equation of line. So over here, I've got the x1 dimension. Over here, I've got the x2 dimension. And using this, I can plot this line. And I can say that anything in this region or beyond the line is the positive example, so class 1, and anything in this region below the line is in the second or negative class. The takeaway from this is that a perceptron provides you with a linear decision boundary. So what form of a decision boundary can a perceptron make? It can form a linear decision boundary.